Today we're going to talk about radical expressions and equations if we can get to it. Okay. Okay, so what do we mean by a radical? A radical simply is the root symbol. Okay, that's what we mean by a radical. And a radical can be a square root, which is typically what is understood when there's no number, but it can also be a cubed root. It can also be a fourth root, fifth root, so on and so forth. And what that simply means is whatever number is under the root symbol is the result of the base number multiplied by the number of roots to get to that number. So the square root of 9 is 3. Why? Because 3 squared gives me the number 9. So the square root is 9. The cubed root simply means there's some number that I multiply by itself 3 times, I cube it, and it equals the number in here. So let's say in this case 27. Okay, what is the cubed root of 27? Well, what we mean is what number do I cube to get 27? Well, that's 3. 3 times 3 times 3. So my cubed root number is 3. So the cubed root of 27, whoops, 27, that's pretty bad handwriting, is 3. Okay, so this is what we mean by radical. We have root symbols and we're trying to find the base. Okay, so many times it's not necessarily straightforward. So let's do a good example. Let's look at the root of 72. Okay. Well, what two numbers, since there's no number here, we're assuming a square root, what number do I have to multiply itself in order to get 72? Well, if we just look at a straightforward approach, I know that if I multiply 9 times 9, I'm going to get 81. So that's a little too high. So let's go one number underneath. What about 8 times 8? Well, 8 times 8 is going to give me 64. Well, here we have a problem because the square root of 72 can't be 8 because it's too small, but it can't be 9 because it's too big. So it's somewhere in between. So how do I do this? Well, we're going to go back to the factor tree. So if we take the factor tree, and I'm going to look for all of my prime roots here, okay? So if you remember the factor tree is simply a tree that we use to find the prime factors of a particular number. And so the first thing I'm going to do here is I'm just going to divide this by 2. That's usually the easiest thing to do if I have an even number. If you know of another number that simply divides in there, you can use whatever you want. It all works out the same. So here I know that if I divide by 2, I get 36. 2 is a prime, so that's going to carry all the way down. 36, though, I know that's 6 times 6. And so here, 2 times 36 is 72. Then here at this level, 2 times 6 is 72. Let's keep going. 6, the two primes that multiply to give me that are 2 and 3. And the two primes here are 2 and 3. All right, so here we have 2 times 2 times 3 times 2 times 3 gives me 72. Okay, so what that means is I could rewrite all this underneath the radical, right? Because the square root of 72, I can write as this. Now I can use this. Let me go ahead and start here, and then I'll go back to why using this might be a little bit easier. Okay, so I can multiply things in any order I want, so I'm gonna put my 3 2's together. The 2, the 2, and the 2, and then I have 2 3's left over. Okay, so notice what we have here. We have 2 times 2, which is 4, times 2, which is 8, and then 3 times 3, which is 9. So what I could do is I could set things up here. Um, let's go ahead and I'll make some very easy squares. So here we have a square, 2 times 2. Here we have another square, 3 times 3. So I'm going to rewrite this as 4 times, and I'm going to go ahead and put the 3 times 3 next, 9 times, and then what's left over there is 2. All right. I'm going to review one of the concepts about a radical, and that is this, that if I have the radical of A times B, that is the same thing as the radical of A times the radical of B. Okay? The radical of A times B is the same thing as the radical of A times the radical of B. So here, the radical of 4 times 9 times 2, I can split the radical over each one of those. The radical of 4 times the radical of 9 times the radical of 2. Okay? The radical of 4 times 9 times 2, as long as they're all underneath the same radical, I can split them up into individual radicals as long as they're being multiplied. Okay? All right. So now we've kind of broken this down to where this is a little easier to work with. The square root of 4 is 2 times the square root of 9 is 3 times, and the square root of 2, we don't have a good number for that. We're just going to leave that as the square root of 2. Okay, 2 times 3 is 6, and then the square root of 2. So what we're able to do, because 9 is too big, 8 is too small, what we have figured out though, what's perfect for this is the square root of 72 is 6 times the square root of 2. And if you were to throw that to kind of look at it from a calculator perspective, 6 times the square root of 2, you could see that that is 8.48. So it is in between 8 and 9, right? Almost halfway between them. And that's the number that, if you square it, is going to give you 72. Square it, I'll get 72. So to write it out exactly, since this is an irrational number, it's a never-ending decimal that always changes like pi. In order to write it exactly, we need to keep it as the square root of 2 and not try to change that to a decimal. Okay, so I showed you I was going to, or I told you I was going to kind of show you something in here. Notice what we can do right here, okay? Right here, 2 times 36. Since I know that 36 is a perfect square, I could have rewritten this as the square root of 2 times 36, because that also gives me 72, okay? So the square root, right? If we had a square root here, we got 2 times 36. Then I split the root over these two. That's the root of 2 times the root of 36. The square root of 36 is just 6. So this is the square root of 2 times 6. I can multiply things together in any order I want. So I'm going to put the 6 first times the square root of 2. So this is a little bit quicker here. If you see a root in there, you can see it right here, right? Here's 6 squared gives me 36. So if you see the root in there, you can use it immediately and get to your answer. All right. Now let's do one like that, but let's add another dimension to it. I'm going to throw in a variable. So let's do 32x squared. And let's go ahead and find the square root of that. Okay. Okay, so I already know that I can split this up over 2. So I can do the square root of 32 times the square root of x squared. Okay, the square root of x squared is just going to give me x. So that'll be pretty straightforward. But let's look at this 32, okay? There's no direct thing that gives me 32 as an easy square, right? 5 times 5, if I look at that, that's 25. That's too low. If I look at 6 times 6, that's 36. It's too high. So this number is going to be between 5 and 6. Okay. So let me go ahead and divide that 32 by 2. 2 times 16. And you may notice immediately, oh, I've got a perfect square in there. So I could go ahead and jump out. But if you didn't notice that, and you happen to divide it by 4, you would see that you do have a perfect square. 4 times 4. These are also themselves perfect squares. Right? So you have 2, then you have times 2 squared times 2 squared, or times 4 times 4, or times 16. So any one of those combinations is okay to use. I'm going to use this one right here, 2 times 16 times square root of x squared. And I'll go ahead and split those two out. Square root of 2 times the square root of 16 times the square root of x squared. This is the square root of 2 times square root of 16 is 4 times the square root of x squared is x. So I can multiply things in any order I want. I'm going to do the 4 first, then the x, and then the square root of 2. That is my final answer. So basically what we're doing is we're simplifying what's underneath the radical into something where we're basically down to a prime underneath the radical sign. All right, let's do one more like this. Let's do the square root of 125k to the third power. Okay, so I'm going to go ahead and split out my 125 and my k to the third. And I also know that k to the third is not a perfect square, so I'll deal with that here in a little bit. But let's at least look at 125. I know that that would split into 25 5 times. And here I see a perfect square. 5 times 5 is 25. So I'm going to use that knowledge. I'm going to use this layer right here. So this square root of 125, I'm going to express as square root of 25 times 5 times the root of k3, k to the third power. Okay, so now I'm going to split my radical, square root of 25 times square root of 5 times square root of k to the third. All right, now square root of 25 is 5 times square root of 5. That's already a prime, nothing I could do to simplify that. But what about this k to the third power? It's not a perfect square. Well, k to the third power, right, is the same thing as k times k times k, right? And two of those k's I could express as k squared. So that's what I'm going to do. I want you to watch kind of how this happens. This k times k, I'm going to make k squared times k. Now, this one right here is a perfect square. The square root of k squared is just k. So let me split this up over the radical as well, so you can see that. Square root of k squared times the square root of k. Square root of k squared is just k. So we have 5 times the square root of 5 times k times the square root of k. All right, so I can multiply things in any order I want. I'm going to put those two together, the 5k. And then I'm going to have the square root of 5 times the square root of k. Now, if you remember the rule that we looked at earlier, the square root of a times b, or the root of a times b is the same as the root of a times the root of b. Okay? So things can happen in the reverse. If I have the root of a times the root of b, if I'm multiplying two roots together, the same type of roots, in this case both squared, I can put it under the same radical. So that's what I'm going to do here. This root 5 times the root k, I'm going to combine and put under the same radical. Square root of 5k. So 5k times the square root of 5k. All right. Next, let's look at adding and subtracting roots. Okay. Adding and subtracting roots. So what would something like this look like? All right, well, let's look at this. We're going to have 3 times the square root of 54 minus the square root of 6 minus 2 times the square root of 45. All right. Now, just like terms, right? We've got 3 terms here. Do I have any like terms? Well, in this case, we have no variables, but roots work the same way. If I have 2 times the square root of 2 plus 5 times the square root of 2, I have 7 times the square root of 2. I can combine those two because they're multiplying the same root. However, if I have 2 times the square root of 3 plus 5 times the square root of 2, I can't combine those. Okay, so what we have to see then is do I have any similar roots between these 3 terms? So with square root of 6, that really just becomes the square root of 2 times 3. And there's nothing I can factor out of that. There's no root I can take out. I don't have a perfect square I can take out. So that's really just the square root of 6. All right, what about 54? Let's go ahead and factor tree 54. 54 I could divide by 9. That's 9 times 6. And then right there, we have a perfect square of 9. So here I have 3 times 54 I can represent as 9 times 6. Then the root 9 I can isolate 3 times the square root of 9 times, look at this, the square root of 6. And then here the square root of 9 is 3. So I have 3 times 3 times the square root of 6. All right, so what I have is 9, that's that 3 times 3 there, times the square root of 6 minus the square root of 2 times 3, or I'll just write that as the square root of 6. So I can actually combine those two now. So let's see about this 45. All right, can I do anything there? 45 is 9 times 5, which is also has a 9 in it, and therefore a perfect square. So here I can do 2 times the square root of 9 times 5. Split that root over the 2. 9 times the root of 5. And I have negative 2 times 3 times the root 5. So negative 2 times 3 is negative 6. Negative 6 times the square root of 5. So here, this last term here becomes negative 6 times the square root of 5. This term here becomes this term here. And then this term here becomes this term here. So let's rewrite this. 9 root 6 minus root 6 minus 6 root 5. Okay, so do I have any like terms, so to speak? And remember, they have to have the same root. So this and this have the same root, but that does not. So I can't combine it with this. This will just have to be left alone. So 9 root 6 minus root 6 leaves me with 8 root 6 minus 6 times the root 5. And that is my final answer. Let me double check that with my notes. Very good. All right. Now let's look at a little bit of multiplication in this case. Okay. What do we do in the situation where we would have root 5 times the quantity root 5 plus 3 root 6? Well, here we have distribution. So we'll distribute this root 5 over that addition, and we will have root 5 times root 5. And then root 5 times 3 times root 6 would be this. Root 5 times root 5, we could put that under the same radical. Same thing here, we could put those two under the same radical. 5 times 5 is 25. Six times 5 is 30. Square root of 25 is 5. Now, can we do anything with the 30? Well, we really can't, even though it looks like we should be able to maybe get something out of it. No matter how we factor tree this thing down, your primes, you're not going to have any squares in here. 10's not a square, 3's not a square, 2, 5. These are all primes. So it actually is just going to stay root 30. 5 plus 3 times root 30. Okay. Let's see if I can get an example here. Yeah, let's try something like this. So let's do a binomial. We're going to have root 2 plus 1 times root 2 minus 2. All right. So in this situation, we're going to do what we've always done. Is we're going to take this and multiply it into my other. We're going to distribute this. So the first one is going to be this times root 2. And then we're going to have this times negative, so it's going to be a minus 2. All right, inside those boxes, we simply have a root 2 plus 1, and that box is a root 2 plus 1. Okay, that's what's inside the box. Okay, now let's distribute this root 2 into this quantity. So we have root 2 times root 2, and root 2 times positive 1 just gives me a positive root 2. And I have minus, or yeah, 2 times, since I have a minus here, I'm going to protect myself by keeping the parentheses and then distributing the negative. So 2 times root 2 is going to be 2 times root 2, and then plus 2 times 1, which is 2. Okay, so now I'm going to distribute the negative. So root 2 times root 2, I could put them under the same radical, 2 times 2. Some of you have already realized that this is going to be 2. Root 2 times root 2 is going to end up being 2, so you can skip that step if you want. Minus 2 root 2 and minus 2. Very good. So root 2 times 2 is root 4 plus square root of 2 minus 2 times the square root of 2 minus 2. All right, root 4 is going to be 2. 2 plus root 2 minus 2 times root 2 minus 2. Okay, now let's look in here and see if we can combine anything. Notice that we can combine as long as they have the same root. So in this case, I can. I have a root 2 minus a root 2, a positive root 2 minus a root 2. So that's basically a 1 minus a 2, which is negative 1. So negative root 2 is what I'm left here when I combine those two. All right, then I have a 2 minus a 2, and those simply cancel each other out. And I'm left with a negative root 2 as my answer. Double check my notes. Good. All right. Then what I'm going to do next is I'm going to look at division. All right, because this is where the radical is going to take kind of an interesting turn, not turn, but it's going to do a few things. So for example, let's look at this equation. 4 divided by negative 5. Sorry, let's not do that one. Let's do one that's a little straightforward. 4 over 4 minus root 3. Now, one of the things in mathematics that is a convention is we never have a root in a denominator. And so what we're going to do is we're going to get rid of that root in the denominator. And you may remember if we had something as simple as 4 over root 3, we could simply multiply the top and bottom by root 3, right? The top would become 4 times root 3. In here, root 3 times root 3, that's root 3 times 3, that's root 9. So 4 times the square root of 3 over the square root of 9. Square root of 9 is 3. So what you're left with is 4 times the square root of 3 over the number 3. So notice how the radical is now in the numerator, whereas before it was in the denominator. And that's what we have to do. But in this case, the denominator isn't a single root. The denominator is actually a binomial. So how do we get rid of that? The way that we get rid of that is by understanding that we can multiply the top and the bottom by the conjugate, okay? So what is the conjugate of A plus B? The conjugate is the quantity A minus B. And what's the conjugate of A minus B? That's the quantity A plus B. So all we're going to do is take the conjugate of this. So this is 4 minus the square root of 3. its conjugate would be 4 plus the square root of 3. Okay, and I'm going to do that both on the top and bottom, because by doing that, these two quantities would cancel each other out, and you're just left with 1, and 1 times this is this. So I haven't changed anything. I'm simply expressing it differently. Okay, so now let's look at the top. I'm going to multiply through the 4. 4 times 4 is 16. 4 times root 3 is 4 root 3. Okay, now this is where I'm going to show you how this cancels itself. So obviously we have two binaries like we did in the last problem that we worked. So we'll do this first one times 4. So that would be 4 minus root 3 times 4. Okay, then we're also going to do this one. So, and this is positive. So 4 minus root 3 times root 3. Okay, so all I've done is take this first binomial and I've distributed over addition here, and I've gotten this. Okay, now I'm going to distribute again. The 4 to the 4 and the 4 to the negative root 3. So 4 times 4 is 16. Whoops, let me go ahead and rewrite this whole thing. So on the numerator, I have 16 plus 4 root 3. Okay, 4 times 4 is 16. 4 times negative root 3 is negative 4 times root 3. All right, now I'm going to come over here. I'm going to take this root 3 and I'm going to multiply it into here. Okay, so root 3 times 4 root 3, that's all positive. So positive 4 root 3. Root 3 times negative root 3 is negative root 3 times root 3. Okay, now here, the 16 stays. So let me switch colors to try to make this a little bit easier to see. So we have 16 plus 4 root 3. Okay, and that's going to be over 16. Now here you have minus 4 root 3 plus 4 root 3. So those two are going to cancel each other. Okay, then you're going to have minus root 3 times root 3, or root 3 times 3. The numerator, I have 16 plus 4 root 3. Down here, 16 minus the square root of 3 times 3. Well, that's the square root of 9, which is 3. So over here, I'll write 16 plus 4 root 3, 16 minus the square root of 9 is 3. Okay, so 16 minus 3 is 13. So I have 16 plus 4 root 3 divided by 13. We double check that that is, of course, my answer, which it is. Very good. Okay. So it's a little involved, but essentially the key takeaway is that we're multiplying by the conjugate in order to be able to get rid of that. Notice how right here we're eliminating the radical. This radical is eliminated because we're always going to be multiplying it by itself, which is going to lead to a number without a radical. All right, we're covering a lot today. So just another quick concept, because it's all kind of related together. And that is now we're going to take this idea and we're going to put it into an equation. So let me, um, all right, so let's start with, now that we're doing equations, let's start with this. So 3 is equal to the root of x plus 10, and then all of that plus 2. Okay, so here what we want to do is we want to solve for x, but while we're dealing now with something we haven't really dealt with before, and that is a radical. So now we have some tools to be able to handle this. So the first thing I'm going to do is I'm going to subtract the 2 from both sides. All right, and that is going to leave me with 1, 3 minus 2. And then over here, the square root of x plus 10. Okay, over here, that 2 is going to cancel. Okay, now what I have interesting is I have something equal to, and everything over here is a root. So what that means is I can take this and I can square it, right? It's a root 2, so I can square it. And if I square the right side of the equation, I have to square the left side of the equation. So this does a couple of things for me. 1 squared is simply just 1. But here, the square root of something squared, what is that? So if we take any number, any expression represented by the letter x, and we take the square root of it, okay? Then we take the square of it, which is what we're doing here, the square root of something, and we're going to take the square of it. Well, if I square this, that is the square root of x times the square root of x, right? That's what squared means. We're going to take this thing, multiply it by itself twice. All right, so that's going to give me the square root of x times the square root of x. Because of what I've already know about radicals, I could put these under the same radical. So this is going to be the square root of x times x. X times x is x squared. And the square root of x squared is simply just x. So if I square the square root of something, it's just the something. So in this case, if I square the square root of x plus 10, what's left is x plus 10. And now I can solve for x pretty easily. I'll go ahead and subtract 10 from both sides. And I have negative 9 is equal to x. All right. Okay. So let's do another one like this. The equation ones can be a little complicated. So let me do one that's a little bit more involved. All right, let's do the square root of 3p plus 11 is equal to the square root of negative 1 minus p. All right, so now I've got a radical on both sides. What do I do here? Well, actually the same thing. I'm going to square both sides. Since everything is a radical, it makes it pretty easy to square because I know that if I square a square root, I'm just left with what's inside. So in this case, a 3p plus 11 equal to a negative 1 minus p. Now I can do some algebra. I'll go ahead and add p to both sides here. So I can subtract, or I can cancel it from this side. 3p plus p will leave me with 4p plus 11 is equal to negative 1. And then I'm going to subtract 11 from both sides. That's going to cancel here. And then I'll have 4p is equal to negative 1 minus 11 is negative 12. And then what I'm going to do is I'm going to divide both sides by a positive 4, which 4 over 4 was going to reduce to 1. 1 times p is just p. So that isolates p on the left. On the right, negative 12 divided by 4 is a negative 3. All right, so let's do another kind of more complicated one. Um, let's do, here we're going to do the square root of 80 plus 2k, okay, is equal to k. And the reason why this one's going to be a little bit more involved is this is actually going to yield a quadratic. Okay, so I have everything under a radical here on the left. So what I'm going to do is I'm going to square both sides of my equation, and the square of a square root simply yields what's underneath. And then on the right, I have k squared. So what I have now is I have a quadratic. I have a k squared, I have a k term, 2k, and a constant. So what I'm going to do is I'm going to subtract 80 from both sides, which is going to lead 2k is equal to k squared minus 80. And I'm going to subtract the 2k from both sides. And I'm left with 0 on the left. K squared minus 80 minus 2k. If I change these to positive negatives, and I can add things in any order I want. So this is k squared plus negative 2k plus negative 80. Take the adding, the negative, and put them back to subtraction. K squared minus 2k minus 80. Okay, so now my leading coefficient is 1. So I just need two numbers that would multiply to give me negative 80, but would add to give me negative 2. Two numbers that would multiply to give me 80, add to give me 2. Let's factor tree this. We have 40 and 2, 20 and 2, 10 and 2, and then this is 5 and 2. Okay. So 10 and, let's see, 2 times 2 is 4, times 2 is 8. Oh, there we go. 2 times 2 times 2, it's 8. 8 times 10 is 80. And then 8 and 10 are 2 apart. So we just have to figure out where those are. So negative 8 times a positive 10 gives me negative 80. And negative 8 plus 10 is a positive 2, not a negative. So let me switch those. So positive 8 times a negative 10. 8 times negative 10 is negative 80. And then 8 plus negative 10 is negative 2. There we go. So k plus 8, k minus 10. All right. So k is either a negative 8 or a positive 10. Negative 8 makes this 0. Positive 10 here makes this 0. So k can be either one. Just double check my notes there. All right, they're saying 10 is the only solution. Let's see why they say negative 8 is not. So let's look at negative 8 here. Oh, negative 8 here. Negative 8 times 2 is negative 16. That's 64. Yeah, I don't understand why -8 is not an answer. Well, actually, if we look at we know that k cannot be a value. You can't have a negative underneath the radical. So if I say 80 plus 2k has to be greater than or equal to 0. Okay, so if I subtract 80 then from both sides, I have 2k is greater than or equal to -80. Divide both sides by a +2, so that doesn't change. K must be greater than or equal to -40, which -8 would do that. Let's see. Oh, maybe it has to do with if we look at the original equation. Okay, look at this original equation. If I plug in -8 here for k, whatever I get in here, it can never be a negative. See, if k is -8, the square root of anything cannot give me -8. That's why it can't be -8. Okay. A square root of something, no matter what it is, must be greater than or equal to 0. So since k is negative, that was not going to work. Okay. So you could see that these get a little complicated. So let's just do one more. I know this video is long, but I feel like this is probably important to understand this. And this will be the last one. X minus 4 is equal to the square root of 7x minus 40. Okay. So here, since I have the square root all on one side, I'm going to go ahead and square both sides, but I've got to square this whole thing. Okay. So the right side's easy. That's just the square of a square root. So that's 7x minus 40. And here, we're going to have x minus 4 times x minus 4. So that's x minus 4 times x. So x times x minus 4. And then we have -4 times, oh, I'm sorry, x minus 4 times -4. So here's -4 times x minus 4. Okay. And what I've done here, it's a little bit, I've wrote it a little bit differently. So this is multiplied by this, but I went ahead and wrote the x first because I can multiply these two things in any order. And then this multiplied by this, which is the -4. So I put the -4 here. Reason I did that is if the negative stays here and I put this 4 over here, then I have to multiply the 4 in, then the negative in. Here I can do both of them together. All right, so what I'm going to do then is here we have x squared minus 4x, and here we have -4x. -4 times -4 is +16, equal to 7x minus 40. All right. Now I'm going to bring everything over here to the left because I have a lot of kind of overlapping or like terms. So minus 7x on both sides here. So this is going to be x squared minus 11x. Oh, I'm sorry. Hold on. Before I do that, I can combine these two. So -4x minus 4x minus 7x. Yeah, so x squared minus 15x, because I combine these two, and then with that plus 16 is equal to -40. So now I'm going to add 40 to both sides. So I'm left with 0 there on the right. And over here, this is going to give me 56. So I have x squared minus 15x plus 56. Okay. Two things that multiply together to give me 56, that add together to give me negative 15. I know that 7 times 8 is 56. So, but it needs to add together to give me negative 15. So negative 7 times negative 8 multiplied together gives me positive 56. But if I add them together, they give me negative 15. So then this ends up being x minus 7 times x minus 8. And this means that x can be either positive 7 or positive 8. Now let's look back to the original. Does this cause any problems? So my original, without the squares here, is x minus 4 is equal to the square root of 7x minus 40. Okay, so here we notice that if we plug in 7 or if we plug in 8, neither one of we take away 4 from either one of these, it's not a negative number. So we're going to actually be okay. We can use both of them. All right.